So good afternoon to all of you. So in this first virtual lab, we are going to discuss about VI characteristics of a diode. In the first year, in basic electrical and that electronics engineering subject, you might be learn the PN junction diode. And now, today we are going to discuss the practical of this PN junction diode virtually. So the title of this our topic, this practical, is VI characteristic. What is meant by this V? V stands for the voltage and I stands for the current. It means that the voltage across the diode and the current flowing to the diode, the graph which is plotting between the voltage and current related to the diode, that graph is called as VI characteristic of a diode. Before proceed further to the actual practical, let me explain that the basic theory related to the PN junction diode. As you already aware about it, when I say that the PN junction diode, it means that the diode which is formed by combination of P-type semiconductor and N-type semiconductor. When these P-type and N-type semiconductor are combined together, then a one crystalline structure is formed, and that entire structure is called as a PN junction diode. So this PN junction diode is made with a semiconductor material. Mainly, the two semiconductor materials are widely used. One is a silicon and another one is a germanium. But out of these two also, the silicon PN junction diode is most widely used. Okay. So this PN junction diode having its a two terminal. One is called as an anode, means positive terminal, and other is called as a cathode. The basic function of this PN junction diode is it will conduct the current only in one direction. It will conduct the current only in one direction. It means that there are actually two biasing techniques, means that there are two ways to connect the diode in actual circuit. We call it a biasing. So what are these two ways? One is the forward bias and another one is reverse bias. Okay. When the diode is connected in a forward bias, it can easily conduct the current. And exactly reverse, when the diode is connected in a reverse bias, it will not conduct the current. This is the basic property of a PN junction diode. And due to this property of a PN junction diode, this diode is also called as a rectifier diode. The basic or the important function of this PN junction diode is in a rectification. Get it, my friend? That's why the another one name to this PN junction diode is a rectifier diode. Actually, as you know that this diode is made with a semiconductor material, so that one can call the semiconductor diode also. As you know that this is the crystalline structure, so that you can call also the crystal diode. It means that there are so many names to this PN junction diodes are given. One is a PN junction diode, another one is a semiconductor diode, another one is a crystal diode, and depending upon as it is used in the rectification circuit, that's why it is called as a rectifier diode also. A simple thing you need to understand and you need to remember, the number one is when the diode is connected in a forward bias, it will conduct the current, means I can say that when the diode is connected in a forward bias, it will act like a closed switch. And another case is that when the diode is connected in a reverse bias, it will not conduct the current. Get it? It means that I can also say like that when the diode is connected in a reverse bias, it will act like an open switch. And as you know that whenever the switch is open, the current can flow through the circuit. And whenever the switch is closed, the current can easily flow through the circuit. And when the switch is open, current will not flow through the circuit. It means that forward bias diode acts like a closed switch and the reverse bias diode acts like an open switch. But the question comes here when we say that the diode is connected in forward bias. So the simple thing is that, as you know that if you see the symbol, this is a symbol of a PN junction diode. If you see the symbol very carefully, you can observe in the symbol a one arrow, and in front of that arrow a one vertical line, we call it a bar. So in this symbol, this arrow represents the positive terminal. So this is the positive terminal, and this vertical line bar represents the negative terminal. Okay, it means that the arrow will represent the p-type semiconductor and this bar will represent the n-type semiconductor. Simple thing is that. And now I say that when the diode is connected in a forward bias, it means that when the p region of a diode, means positive terminal of a diode, when it is connected to the positive terminal of an external battery, DC battery, that time, or that n region of a diode, when it is connected to the negative terminal of a battery, that time we say that diode is connected in a forward bias. And exactly reverse, when, now see that this arrow means p region, it's a positive. When the positive terminal of a diode, when it is connected to the negative terminal of external battery, and the bar which represents the negative terminal of a diode, when it is connected to the positive terminal of external battery, that time we say that diode is connected in a reverse bias. As I already explained that when the diode is connected in a forward bias, so definitely it will conduct the current, means the current, it will start its journey from positive terminal, it flows through the diode and it will return to the negative terminal. So this is the basic property of electric current. Similarly, when the diode is connected in a reverse bias, it will not conduct the current, it will act like an open switch. It means that the positive terminal, from the positive terminal, no current it will flow through it, theoretically. Practically what happened? Practically, when the diode is connected in a reverse bias, a very small amount of current, negligible amount of current it will flow due to the minority carriers. And the minority carriers in the PN junction diode are very less in number, so that the current is very less. I think is in terms of microampere or nanoampere, means very small current, and that current we call it a leakage current, because what is the basic function of a PN junction diode? It will conduct the current only in one direction, and that to be in a forward bias. But practically it is observed that in the reverse bias also the very small current it flows, and that's why we call it a leakage current. Get it? And this current is not depends upon that external voltage. And now we have to see that how actually the PN junction diode is to be function, is to be operated, or how it works when it is connected in forward bias and when it is connected in a reverse bias. Now please have a focus on that, the forward bias PN junction diode. See the circuit diagram. If you see the circuit diagram, you will observe that this arrow means positive terminal of a diode is connected to the positive terminal of a battery, and this bar means vertical line is connected to the negative terminal of a battery, means the diode is connected in forward bias. When the diode is connected in a forward bias, as you know that the width of the depletion region is get reduces, and the majority carriers can flow from P region to the N region, so that the current can flow through the forward bias diode. But as the barrier potential is exists in the PN junction diode, do you know that the barrier potential which is exist in the PN junction diode, the value of this barrier potential for silicon diode is 0.7 volt, and for germanium diode is a 0.3 volt. And this barrier potential is always avoid or is always create the barrier to flow of free electrons from one region to another region. Means, suppose I say that this external voltage Vs, when it is less than barrier potential, when the external voltage Vs is less than the barrier potential, no current will flow through the forward bias diode. But when this external voltage is goes above the barrier potential, the barrier potential will reduce to zero and definitely current can flow through it. So what you can remember from this discussion? You can simply remember that suppose if it is silicon PN junction diode. So for the silicon PN junction diode, what is the barrier potential? Let's we assume that 0.7 volt. Means from that external voltage from 0 to 0.7 volt, no current will flow through the diode. But when that external voltage Vs having its value above 0.7 volt, the diode can conduct the current very easily. And then you will get the sharp curve. But up to the barrier potential, no current will flow through it. So this is the basic theory behind the forward bias PN junction diode is that. If you have that any doubt, you can raise the doubt. Otherwise, I will continue with the PN junction diode with the reverse bias. Yes, please. If you have that any doubt, please put the doubt. Okay. And now see that the theory behind that the PN junction diode when it is connected in reverse bias. When we say that diode is connected in reverse bias, when the positive terminal of a diode, when it is connected, you can see the diagram to the negative terminal of a battery, and the negative terminal of a diode, when it is connected to the positive terminal of a battery, that time we say that diode is connected in reverse bias. So what happened when the diode is connected in reverse bias? Definitely you already learned the theory. When the diode is connected in reverse bias, the width of the depletion region is increased. And as the barrier potential is increases, no free electrons will move from P region to the TN region. So that theoretically, no current will flow through the reverse bias. But as I explained already, practically it is observed that due to the minority carrier, a very small current in terms of micro or nano ampere can current flow through it, and that is the negligible amount is that. So that's why we say that when the diode is connected in a reverse bias, no current will flow through the reverse bias diode is there. Get it my point? So this is the theory behind the forward biasing and the reverse biasing. Now if you see the graph, see that this is the graph for forward bias PN junction diode. If you see that along that x-axis, we have considered the forward bias voltage across the diode, and along y-axis, we are considering a current flowing through the diode. But now if you see that from 0 to 0.5 and above, the no current, you will observe that no current is flowing. It means that up to the barrier potential of the PN junction diode, though you increase the forward bias voltage, no current will flow through the diode. But once the forward voltage goes above the barrier potential, then you will observe that you will get a sharp curve or sharp increase in current is there. Have you observed it? Means in between 0.5 to 0.6, there is a barrier potential here. And here we consider that it's an approximately 0.6 or 0.7 volt for silicon diode is there. You can read it here, 0.6 volt for silicon diode is there. And now you can observe that from this 0.6, you will observe that the sharp current will flow. For very small increase in forward bias voltage, the current can easily flow through the diode is there. This is the basic property of the forward bias diode. Means what you can remember, up to the barrier potential. Now here you can see that this is the knee voltage. What is the knee voltage? is the voltage from which the current of a forward bias diode increases sharply. That voltage we call it a knee voltage. So you can see that in between 0.5 to 0.6, and or approximately we say that the 0.6 is the knee voltage for the silicon PN junction diode is there, because after the 0.6 the current can easily flow through it, and before the 0.6 current will not flow through it. So this is the forward bias, the PN junction diode is there. Now see that this is the graph for the reverse bias diode. Now if you see that for the reverse bias diode, the no current will flow through it. But now if you see, observe this graph, you may think like that. So this is the forward bias diode graph for the germanium diode. Okay, now I will show you. Actually, if you see that this is the graph where in between 0.2 to 0.3 the current it will be increases, because this is the forward bias diode graph for the germanium diode. Before that I have shown you the forward bias diode graph for the silicon diode, because for the silicon diode the barrier potential is 0.6 volt, so that from the 0.6 volt you will observe that current can easily flow through it. But for the germanium diode the barrier potential is 0.3 volt. So now you can see that from the 0.3 volt you can observe that the current can sharply flow through it. But as you know that in the reverse bias diode the no current will flow through it. Is it right? And now the same things I will try to show you with this virtual lab is there. So this is the theory behind the title VI characteristic of a PN junction diode is there. Now how to do the practical for it, the procedure is given. I will provide you the website of this virtual lab. You can directly, the no ID and password is required to observe this lab, to use this virtual lab. So you can easily read, you can easily use this tab virtual lab. Okay, so the procedure is given for forward bias as well as for the reverse bias. Now I will directly show you the simulation here. Now see that how the PN junction, one PN junction diode, it will be work in a forward bias as well as in a reverse bias. Now let me try to show you the forward bias diode, the forward bias silicon diode. Now if you try to click on that the simulation part, you will observe these types of a window. Here in this window the four things are there. One is the instruction. Have you checked it? When I just keep my cursor on that instruction part, that instruction will pop up. So there are total 10 instructions are given. Another one point is observe, you can observe here the experimental table. We can also call as an observation table. Then third one is that experiment circuit diagram. And this one is the control. How with the help of this control window, I can show you how the silicon PN junction diode it works. Okay, now see that what is the first instruction? Set DC voltage to 0.2 volt. Now if you observe the circuit diagram, here this is a PN junction diode, and to this PN junction diode a 1 voltmeter is connected. This is a voltmeter. This voltmeter shows the voltage across the PN junction diode. And as you know that the basic theory, voltage always measure in parallel with that component. As I want to measure the voltage across the diode, that's why the voltmeter is always connected in parallel with the diode. So this voltmeter gives the voltage across the PN junction diode. Now a 1 meter is connected in series with that diode, and that meter we call it an ammeter. You can see that this is that ammeter which will measure the current flowing through that diode. So the theory, basic point behind to measure the current is that the current is always measured in series. That's why the ammeter is connected in series with that diode. And this is a 1 current limiting resistance. which is required in series with the diode, so that this resistor will avoid the damage of this p-n junction diode. That's why I say that this is the current limiting resistance here. Okay, and now I will try to show you how this experiment it actually works. Is it right? Now see that the first instruction is set the DC voltage to 0.2 volt. Now I will try to select the PN junction diode first. Okay. Now if I select the PN junction diode, this is the title of that diode 1N4001. There are so many PN junction diodes are there. But out of that, if I try to select one, then have you observed that it automatically comes the forward bias voltage? See that now the voltage it will not observe here. But when I click on the diode here, then it's a forward bias voltage, means the maximum barrier potential of that diode is a 0.6 volt. Then I will try to select that the resistance. Okay, let me try to select that 500 ohm. Okay, so see that this is the 500 ohm. You can see that approximate 500 ohm. Now our first instruction is set DC voltage to 0.2 volt. Now I will try to select the DC voltage of 0.2 volt. See that. Now the applied voltage to the PN junction diode is 0.2. The maximum for the barrier potential of that diode is a 0.6. Now that time you can observe that no current will flow through it. Why? Because the external voltage is less than the barrier potential. Now I will just try to add this reading in the table here, because you can observe here this meter shows the 0 reading, voltmeter shows the 0 reading, and that ammeter also shows the 0 reading, because the no current will flow through the diode, so that voltage across the diode is also 0, current flowing to the diode is also 0, but our external voltage is 0.2. Okay, so we are take the reading of the two things, the voltage across the diode and the current flowing to the diode. So here you can see that serial number forward voltage across the PN junction diode is 0, this meter reading, and the current flowing to the diode is also 0. Now let me try to increase that voltage. Now I will take it. Okay, see that up to 0.5. Have you noticed that the reading here? No, so I can add it here. Give me 1 minute. Okay. Now I will take it, the reading 0.5 or 0.6 up to the 0.6, no current will flow through it. See that now my external voltage is 0.5. That time also you can observe that the voltage across the diode is 0 and the current is also 0. Let me try to add this one point also. Okay, now let me increase that voltage. Now see that when my external voltage is 0.7, means it's above the barrier potential, you will observe that the certain value of voltage and the certain value of current. Now the current it starts to flow through the PN junction diode. Let me try to add it. Now let me once again increase that external voltage. You can observe that the voltage across the diode as well as current flowing to the diode, that is also increased. See that. Let me take that the so many readings here. I just try to increase that the voltage, and you will observe that the voltage as well as the current flowing through the diode, it goes on increasing once the forward voltage is above the barrier potential. Now you just have a look on this experimental table. When the external voltage is less than the barrier potential, that time the voltage across diode is 0 as well as the current flowing to the diode is also 0. But when the barrier external voltage is above the barrier potential, you will observe that the voltage also appear across the diode, as well as current, it will start to flow through the diode. And once the external voltage is above the barrier potential, from that point, current is sharply increases for very small change in the voltage across it. You can observe here. Get it, my point? So this is the basic theory behind the PN junction diode is there. And now, if I want to plot the graph with the help of this experimental table, experimental reading, I can see that the graph also. Now, so you can see that this is the graph. If you try to compare theoretically also, you will get the same type of a graph, and practically also you will get the same type of a graph. Means our theory will perfectly match with the practical thing with that. So from this practical reading, if you observe the graph, so you can see that from the 0.5 onwards or at 0.6 onwards, you will observe that the current will be increases. Then definitely the question comes in your mind, can we increase the value infinitely, the external circuit, external supply voltage infinitely? So that answer is no. Why no? Because there is a certain limitation for the forward bias diode. It can conduct the current up to the certain value. If the current will go beyond its maximum limit, then due to the overheating problem, the diode, it may get permanently damaged. So that whenever we have to connect the diode practically in a circuit, that time we must know that how much maximum current can flow through that particular diode, and the diode name is IN4001, and how much maximum voltage we can apply to the PN junction diode. So in this way, you can check, you can cross check the properties, the function of a forward bias diode is that. If you have that any doubt, you can raise the doubt. If not, then I can proceed further. Yes, please. Okay. And now let me try to go for the reverse bias diode. Now see that this is the circuit diagram for the reverse bias diode. Now, if you see that, why I say that reverse bias, because the positive terminal for diode is connected to the negative terminal, and the negative terminal of a diode is connected to the positive terminal. Remaining thing is the same. A 1 voltmeter is connected in parallel to the diode, and 1 ammeter is connected in series with the diode. Now, what the theory says about the reverse bias silicon PN junction diode, no current will flow through it, or practically we say that very small current it will flow through it. So let's try to read that the instruction. The instruction is set the DC voltage to 0.2 volt. Let me click on that DC volt. I will select to the 0.2 volt. Okay, select it. Then second is set the resistor and select the diode. Now let me try to click on that resistance, and I will select that the value of resistance. Let me take it to 1000. Okay, approximately 1000. Then I will select that the same PN junction diode. So maximum reverse bias voltage is a 30 volt. Okay. Now, when the external voltage is 0.2 volt, now you will observe that a certain value of a minority current you can observe here. Okay. Actually, theoretically, we say that no current will flow through it. But as I already explained that the current will flow due to the minority carrier, and this current is remain constant. That's why we say that reverse saturation current, or we call it a leakage current. And this current, whatever the reading it observed in this diagram, in this box ammeter reading, this current is always constant. It will not change it, and it is not depends upon this VDC, means external voltage. Now I can show you. Let me try to add these things first. Now let me try to increase that external voltage. You can see that the voltage across the reverse bias diode it get increases, but the have you noticed that the current it is increases? No, it will not increases. The value of a current is remains same. See that. That's why I say that, and that value of a current is exactly very small, 0.1 microampere. Micro means 10 raised to minus 6, because the no current will flow through the reverse bias diode is there. So in this way, if you observe that the current flowing through the PN junction diode, it's remain constant. That's why it is called as a reverse saturation current. Saturation current means it will not increase, though you increase the external voltage, reverse bias voltage, then also the current flowing through the reverse bias diode, it's not increases, and that current is having it's a very negligible value, 0.1 micro means 10 raised to minus 6 ampere. So this is the property of a silicon PN junction diode is there. If you try to plot the graph, let me click on that, the graph tab, definitely you will see that the graph. See that. Though you increase the reverse, now this minus sign indicates the reverse bias voltage. Here minus sign indicates the reverse bias voltage. Though you increase the reverse bias voltage, you will observe that current it will not increases. The current is almost constant. That's why this current is called as a reverse saturation current, and this current having its very small negligible value. In this case, you can observe that that value is 0.1 microampere is there. Is it that clear? So this virtual lab will clear the concepts about how the PN junction diode, when it is connected in forward bias, how it actually works, and when it is connected in a reverse bias, how it actually works. With the help of this simulation part, now hope that your concepts about the forward bias and the reverse bias, that is nothing but the VI characteristic of a PN junction diode, it may clear. So if you try to see that, the title is very simple, vlabs.ac.in. You just click on the vlab.ac.in, that definitely that virtual lab, the application, it will be observed. You just click on it, go through it. Let me try to show you. See that I just type it vlab.co.in. This is the main website, vlab.co.in. You can take the screenshot of it, or you can take a note of these things. vlab.co.in. If it is open, then below that you will observe that electronics and communication. When I click on it, then the virtual lab practicals of different institutes. You can see here IIT Kharagpur, COAP Pune, all different practicals it get opened. In that, so many practicals are there. Out of that, you just click on basic electronics practical, because our topic is related to the basic electronics. So the basic electronics practicals part will be open. In that, here you can observe that the list of experiment. When I click on that list of experiment, you will observe that the total 17 experiments are here, and out of that, as per your syllabus, I have selected this one topic, VI characteristic of a PN junction diode is there. And in that, you will observe that the so many parts, theory part, procedure, simulation. On this VI characteristic of a diode, one quiz is also there, one assignment is also there. So it is expected from the student is that the student should read that the theoretical part as well as the procedure part, and do the simulation, try to check that whether the theoretical part and the practical parts are matched or not. And once after the simulation, once your concept will be clear, then you can directly go through that the quiz